Today, I would like to talk about the data compression and encryption. We said that for transmitting the data, because the size of some data files are so large, we need to compress them, and also because of the security issues, especially in the wireless environments, we need to encrypt the data. So today we want to learn that how can we compress the data and also encrypt it. If you remember, the first block in the block diagram of data transmission was source. The task of this block is producing data, but sometimes the quantity of data is large. So transmitting the big data is too difficult. To solve this problem, we need to compress the produced data before transmitting them. Therefore, we can say that data compression methods reduce the quantity of data without any loss of information. This sentence is so important. The quantity of data reduce the quantity of data without any loss of information. Okay, generally, we can consider two approaches to data compression. The first one is lossless compression, and the second one is lossy compression. In lossless compression technique, all of the information will maintain in original data. These techniques are used for compressing numerical data, such as monetary account information, computer codes, and so on. One of these techniques is called Huffman coding. I will talk about the Huffman code, and you will learn that how can we compress the data using Huffman code. In the lossy compression technique, some loss in information can occur. For example, we can have lost information in audio data or image and so on. Okay, before compressing information or compressing the data which is produced by source, we need to model it. But how can we model the information? The answer of this question is using probability theory. In fact, because information contains an element that we don't know previously, it means that we have to use probability theory. Now, we suppose that source has a vocabulary of M symbols represented by xi. This xi is our symbol. And this symbol can be x1, x2, up to the xm. The size of source symbols is m. Okay, look at here. Suppose that this example, for example, hello. Okay, suppose that in our text we we have written hello. Now each symbol has a probability of occurrence. This is x1, this is x2, x3, x3, x4. For example, look at here, good, x1, x2, x3. Okay, if I want to calculate the probability of x1, is 1 divided by 3. P x2 is 1 divided x2, x is 2 divided by 3. If m symbols are equally to occur, the probability of any one symbol is like that. P x1 is equal to P x2 is equal to P x3 up to P xm is equal to 1 divided by m. For example, look at here. This is my text. This is my file, data file. How many symbols do I have?
5.
M is 5. And what about the probability? Px1, Px2, up to Px5, all of them, because all of the occurrence are the equal, it means that all of the probability of symbols is 1 divided by 5. Now let's talk about the source entropy. What is the source entropy? Actually, for some reasons, we need to quantify the average information, which is produced by source. This task is done by calculating the source entropy. Okay, for quantify the average information, we need to calculate the source entropy. So if a source produces the symbols x1, x2, x3 up to the xm with probability of p of xi, so we can define that the source entropy is computed using this formula, minus summation of probability of xi times log to the base of 2 of p xi. Using this formula, I can calculate the source entropy, and this source entropy indicates the quantity of the average information. In fact, we can say that this entropy H of Hs indicates the average number of bits that we require to represent these symbols as a binary code. The m equally probable symbols, if I have the m symbols with the equally probability, we learn that pxi is equal to 1 divided by m. Now using this formula, hs is equal to log 2 of m. If I calculate the logarithm of m in the base of 2, it means that I can calculate the h of s. Now look at here. Consider the source generates random bits x1 and x2. px1 and px2 are the same and is equal to 0.5. For calculating the entropy of source using this formula, my m is 2. It means that I is equal to 1 up to 2 pxy log 2 px1 minus px2 log 2 px2. I know the probability with substituting 0.5 instead of px1 and px2 as you see here, and calculating this value, I can find that 1 bit per symbol is my average number of bits that I can use for transmitting produced data from source. Using h of s, I can find the average number of bits in source. Now, as you saw, if we know the probability of symbols, we can calculate source entropy. But sometimes we don't have any information about the probability of symbols. So we need to estimate it from the data file. Now, suppose that we have a data file with size of nt. My data file is the size of data file is nt. This data file contains mx symbol. That mx is less than nt. I want to calculate the effective probability. Effective probability. Now, if the file contains decimal digits, suppose that my data file contains 0, 1, 2, 3 up to 10. It means that mx is equal to 10. Why? Because my different symbols number is 0 up to 9. It means that I have 10 symbol. mx is equal to 10. So this file contains nx size, for example, 1 million. Or if the symbols are represented with ASCII 7-bit code. So we will have x1 up to 128. We know that with 7-bit we can represent 128 numbers. But maybe the n of t can be 10 to the power of 6 billion million, can be the size of data file. Now, for calculating the effective probability, for calculating the effective probability. We suppose that xi occurs ni times, and the size of file is nx, is nt. We can define the effective probability using this formula. Ni divided by nt. The size of data file. Ni is the number of occurrence of xi. Okay, now we can say that for a data file with unknown symbol probabilities, we use the effective probability to compute an estimate of the source entropy. Now, because I use the effective probability for each symbol, I need to calculate effective source entropy. And the effective source entropy is calculated using this formula. And we call it h hat of s is equal to minus summation of effective probability of symbol times log 2 effective probability of symbol. Consider we have a binary data file containing 1000 bits. That 600s are 1, 400s are 0. Now, my mx is 2, so for calculating the effective probability of 1, I say that 600 divided by 1000, which is equal to 0.6, and for 0 is 0.5. 0.5. Now, after calculating the effective source entropy, we need also find the effective file entropy, which is denoted by h hat of f. H hat of f. Now, this h hat of f represents the minimum number of bits that are needed to encode or compress the file. Minimum number of bits that we need to encode the file. Look at this example. Suppose that this is my data file, A, B, A, D, A, E, C, D, D, A. There are 5 different symbols. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols, but I have only 5 different symbols. What are these different symbols? A, B, C, D, and E. So, because the number of all of the symbols are 10, it means that my size of data is 10. Now, for calculating the effective probability, I learned that PE of A is NA divided by NT. How many A symbol I have here? 1, 2, 3, 4. 4 divided by 10. 0.4. How many B symbol do I have in my data file? 1, 2. 2 divided by 10. Up to the end. For C, 0.1. For D, 0.2. For E, 0.5. 1. Is it clear up to now? Did you understand how can
Yes,
I calculate the effective probability?
Yes.
Okay. H hat of S is equal to minus PE xi log 2 PE xi. Mx is 5. It means that PEA, PEB, PEC, DE. I calculated all of the probabilities with substituting this value instead of PEs. I can find that effective source entropy is 2.12. What does it mean? Now, I want to calculate the effective file entropy with multiplying the file size into the H hat of S. I can find the effective file entropy 21.1. This means that 10 symbols in that file can encode and compress using approximately 22 bits. Look at here. Suppose that I have A, B, C, D, E. How many symbols do I have here?
5.
Nx is 5. Now, for representing these symbols x1 up to x5 in binary number with bits, with binary numbers, minimum how many bits do I need?
15.
No, for each symbol, minimum how many bits do I need?
3.
3. Why?
Because we can determine 4 by 3 bits.
Because you have 1, 2, 3 up to 5, and you have 5 different symbols. For representing 1 up to 5, minimum you need to have 3 bits. If you have 4 symbols, how many bits do we need? 2 bits. So, because here I have 5 different symbols, minimum I can represent each symbol with 3 bits. For example, I assign 0, 0, 0 to 1, 0, 0, 1 for B, 0, 1, 0 for C, 0, 1, 1 for D, and 1, 0, 0 for E.